Hello, and what we're going to do today is we're going to do Unit 2, Section 2, Oceanography, and where we talked about the Big Bang, creation of the universe last time, ending up with the three types of rocks. And today I'm going to talk about how these rocks do change and how we're going to talk about how we get the material into the ocean to make it so much different than fresh water. But anyway, we're going to start with the rock cycle. And when the rock cycle actually starts, anytime I take molten rock, it can be inside the earth intrusive or outside the earth extrusive, and the process called cooling, or we can start making sedimentary rock that can be large grained if it was inside slow cooling, and it can be very small grained or maybe non-existent grain. And I mean, you can actually see the individual minerals that make up the rock if it cools very quickly. Then we have a process called weathering and erosion, which turns the rock into sediment. Then we have lithification through a process called compaction and or cementation, turning it into sedimentary rock, where we actually take the rock and we submerge it or push it back underneath the earth, subject it to heat and pressure, where we cook the rock without melting it, and then we turn it into metamorphic rock, where we can actually get more heat, turn it back into magma, start the process all over again. It's a very cyclic view. This one doesn't really talk about its complexity because we can really go from an igneous rock to a metamorphic, and we go from igneous rock and melt it, go back into igneous. We can take sedimentary rock, weather and erode it, back into sedimentary rock. So we can just keep going back and forth. So it gets a little more complicated in a real true rock cycle. Here's a better view of a rock cycle, a little more complicated. If you actually go to this site right here, you can actually see an interaction of these, but you can see we have heat and pressure making metamorphic rock, we have melting into magma, we have cooling for igneous rock, we can melt it back into magma, we can heat and pressure it back into metamorphic rock, where we can take it and weather and erode it, turn it into sedimentary rock, or we can actually do that same process back in there. We can take the igneous rock, but you can see it goes from anywhere to anywhere on here. This is one that's actually coming from Rocks in Your Head. It's a program created by a friend of mine, and Jane actually has this figure up on her website, and she actually has it in a poster view too. But if you take a look at it, we start with molten rock inside the earth, magma under high heat and pressure, and if that was to actually solidify down here, we would end up with a granite, and that granite can get cooked and turn into a piece of gneiss. It can also change other rock like limestone, which is laid down inside of very deep water, very deep clear water, turn that into marble. It can take shale, which is fine-grained sedimentary rock, usually found farther into the ocean than the beach environment where you get sandstone. We can turn that into slate, sandstone into quartzite, and we can turn conglomerate into metaconglomerate. Conglomerate is actually large size pieces, pebbles and larger, that gets solidified by high steepness or highly steepened slope, like landslides or mudslides or whatever. We can have igneous rock intrusive, which is called phaneritic. We can have igneous rock extrusive, which is called aphanitic. Um, we can have pumice, which is like sponge stone. We can have scoria, which is sponge stone, except it's made up out of darker, denser mafic type rock, which makes up ocean floors. We can have obsidian, which is very shiny volcanic glass, but it actually shows you quite a lot of things that are going on in the rock cycle. Next slide talks about minerals. Minerals are anything that's naturally occurring, not man-made, inorganic, not alive, never was alive, with a set chemical formula like sodium chloride, and atomic structure with sodium and chloride, and usually it's found in an aggregate of a whole bunch of different minerals. The most common mineral of the 6 types that are found on the planet are called silicates. Silicates are created by a silicon tetrahedron. This is a large view of it, and here's a smaller view of it. But basically we have a silica surrounded by 4 oxygens. That's why it's called SiO4. And it actually can be found as a single line, which makes up a majority of the mafic type minerals. It can actually be found in a double line. It can actually be found in a sheet format, or it can be found in a non-individual shaped format like quartz. But these make up the minerals that make up most of the material that's on the outside and inside of the solid rock, Earth. the solid part of the Earth. Then the atmosphere, and you can see we have a picture of the black and white smokers down underneath the Earth, close to the divergent mid-ocean ridges, where we actually put material up from inside the Earth. You come out as steam, but there are compressed gases in there that will eventually go up to the surface. So we have outgassing of outgassing of volcanoes both inside and outside the Earth, producing water vapor and carbon dioxide, all kinds of different materials, some of them very poisonous, probably with our first atmosphere. And it can also get released by some process called partial melting, and partial melting happens when we actually get a magma, and the magma's got all kinds of different minerals inside of it, and as it cools, the ones with the highest melting temperatures actually solidify, and it actually makes the resulting magma blob more felsic, and the magma, the mafic part of it stays solidified, and the mafic magma rises up to the top, and it can have compressed gases inside of it too, which gives rise to this volcanic outgassing. Oceans. Ocean water was probably released by volcanic outgassing. It condensed to form water. When we had our initial very hot Earth, it stayed as clouds. But as it actually was able to drop and cool the planet, it started making an ocean probably about 4 billion years ago. And then the oceans are found on other planets, other moons. The distance from the sun, if it's too close to the sun, liquid water will not form. It'll all be gas. If it's too far from the sun, liquid water won't form. It'll all be ice, or it can be in the Goldilocks zone where we live. It can also be controlled by rotational period of the planets or the moons, and it does help cause a natural greenhouse effect, which allows us to trap some heat, which makes us cooler on the dark side of the Earth as it rotates, and warmer. How about cooler on the bright side and warmer on the dark side? Actually acts like a blanket. You can use a blanket to walk through a fire to keep you cooler, and you can certainly use a blanket on a cold evening to keep you warm. Here's some liquid water found in the solar system, and I did show you this picture, or a picture like this, that didn't have the water on the Earth, but it actually showed if you moved all the water in one location, it's not very much. You can see Europa actually has more water, and Titan has more water than the Earth does. So it's a very, we can find liquid water elsewhere in the solar system. And talking about distance from the sun, if you take a look, we have Mercury, which doesn't even have an atmosphere that boiled away. Venus with a very thick atmosphere, but so warm that you wouldn't find liquid water. We actually have the Earth, as well as Titan and Europa, which do have liquid water. And then we have Jupiter on the far end, which actually could have had water and may have water inside, but it's a gas planet, and then it's way too cold out here. This was supposed to be a picture of a greenhouse. Looks like my animations are a little off, but you understand a greenhouse. Greenhouses can actually hold plants when it's colder outside because the sun is trapped inside the glass. Earliest atmosphere was probably very much like volcanoes, volcanic eruptions. It was dominated with carbon dioxide, water, nitrogen, and some really noxious and toxic gases as well. But our first atmosphere had no oxygen whatsoever, and you can see that the ocean started at 4, Earth at 4.6, oceans at 4, and now we're at 3. And then you can see we almost make it to 2 and no oxygen, and then all of a sudden we start getting oxygen, and then it actually moves all the way up. We used to have higher amounts of oxygen, and this is basically what we call our atmospheric oxygen, or 21% of the atmosphere. So you can see it was a little higher there, it was a little lower there, and right now it's at 21%. Here are a couple of other little steps in it, and it actually talks about the cyanobacteria, and then eukaryotes pop in, and then we have algae and bigger plants, and you can see each one of those actually started putting large sections of oxygen in the air, and then it eventually levels out after each one of those events. Modern atmosphere has mostly nitrogen. 79%, oxygen around 21%, and argon and water vapor, carbon dioxide. So when we actually talk about carbon dioxide in the air, it's way less than 1%. But our initial atmosphere probably came from this volcanic outgassing. Then we have photosynthesis kick in. It started with the cyanobacteria, but all the plants today, where we take carbon dioxide out of the air, we take water out of the ground, and then we actually take light energy through a pigment called chlorophyll, and in a process called photosynthesis can make carbohydrates, C6H12O6, glucose, plus oxygen. And plants need oxygen just like we do. They go through cellular respiration just like we do. They just produce more oxygen to benefit us, and they produce the sugar for themselves, but they produce more sugar so we can actually harvest it as a heterotroph rather than the autotroph plants. Ocean salinity, if you ever tasted the ocean, it is definitely salty. Okay, the primary salt in it is sodium chloride. Makes up most of the salt that's in there, 3.5% in normal ocean water, although it can get a larger percentage or less percentage depending on lots of things. But you can see the chlorine, the chloride and the sodium actually come together. The chlorine ion and the sodium ion come together in a 1-to-1 ratio, sodium chloride, and they make up most of what are called sea salts, but we have magnesium chloride also, and we have sulfates, and we have calcium chloride and potassium chloride and other type of constituents inside there also. But you can see by far sodium chloride is the most common salt. How does it get into the ocean? Rain actually falls on land. It dissolves through a process of weathering and erosion rock. There's some sodium and chloride ions in that rock. It goes down into the water, ends up in the ocean. The water actually evaporates out. Salt remains behind, and it gets more and more salty. Volcanic gases, the underwater vents, volcanoes on the ground, volcanoes in the ocean are all the depositing ions in the ocean water, as well as creating new rock. Dissolved ions will precipitate out. We have plants. This is a Nautilus shell. If you remember that Nautilus that was swimming through the water, you can actually see these little compartments. The Nautilus used to be very small, and it actually gets bigger and bigger and bigger and bigger. And as this was its shell, this section right here, it probably extended to that point. And then every time it actually gets a growth spurt, it pushes itself farther and farther. And right now, the Nautilus would be living in this section of the shell. You can see it grows with time. If you ever looked at a clam shell or a Nautilus or any kind of shell, basically, it has these growth marks on it. So clams start out being really small, and then they have these lines showing the growth spurts. It gives a rougher type appearance to the shell. Inside the shell, in both these cases, they actually put a mother of pearl. This is what we actually make pearl, or what they make pearls out of, and what we can make pearls. They make this so it's all nice and smooth to them. If they get an irritant in it, like a piece of sand or something else in it, they'll actually wrap this mother of pearl around it, which is what we actually use to make our pearls. And ocean salinity is in balance. The input of ions and the output of ions tends to be about the same. Here's a picture of volcanoes and vents putting stuff out, sea spray pulling salt out, volcanic precipitates bringing sodium and chloride and sulfates in, river discharging lots of different ions, biological processes pulling them out, actually making sediments, manganese nodules being an example. So all the yellows, these are processes of removing ions from the seawater, and all the reddish type arrows, that's actually putting it into the seawater. Mass balance and cycling. If we talk about eroded material and crystalline rocks going into the ocean, we have an atmosphere, we have an ocean, we have sediments, and it's going into each of these things. Primarily it's sediments, but it does dissolve ions, and it does actually go into the air as particulates as well. But water in the ocean, primarily from the Earth's mantle. Salts in the ocean, primarily coming off the rocks from land. And salts in the ocean, primarily coming from volcanic activity, both minor, like the black smokers, and very large, like plate tectonics. Moon's creation. Moon formed about 4.5 billion years ago, so very soon after the Earth. The Earth was still being plastered. It was still a non-ocean. It was still a molten planet, but a planet-sized protoplanet about the size of Mars today kind of sideswiped it. And what it did is it threw material out and actually created the Moon. And if you take a look at this picture, Moon used to be a lot closer to the Earth too. It's actually getting farther and farther away. And I'm going to show you a really quick YouTube video.
Everest is the movie event like nothing you have experienced.
Well, apparently after 30 seconds, so I'm going to go back into this and I'll come back to it. And that's where we're going to stop, so you can see we're close to the end.
Based on an incredible true story.
If anyone don't like it, you can.
It looks like a neat movie. Wish I could skip it. Got to get an ad blocker.
Everest, now playing in theaters everywhere. Rated PG-13.
Okay, these are all the planetesimals coming in, and you can see they're going, some are faster and some are slowing, and they're actually running into each other, making larger and larger planetesimals. Sun is forming, Earth is getting larger, more planetesimals running into it. You can see it's got some cooler sections, very thin, but still very molten. Not exactly sure what this view is telling you other than it's really hot. Inhospitable, no life, no ocean. More hotness. Okay, and here comes Mars, or a Mars-type planet. Earth minding its own business. And what happens is they sideswipe each other. I'm sorry, there's the Mars-type planet. It pulverized a lot of the Earth's surface. And one theory about the Moon actually seems to be made more of Earth crustal rock than the mantle rock. And probably what happened is the outside of the Earth actually got thrown up into space. And then it actually made a quick little band. And we can do this with computer animations, talking about the physical property of protoplanets. And then what we think happened is that within a period of about 100,000, maybe a million years, the Moon actually moved around its orbit, sucking in all these protoplanets, getting larger and larger and larger, but it cleaned its orbit. You can see as the orbit gets lesser and less and less. And then they're going to show this very quickly. Cooling, it is going to get impacted with lots of other craters, and then we have the Moon as we think the Moon is today. Eventually we started getting water forming on the Earth, and now we have the Earth. Moon is still up there. Okay, that's all she wrote. I appreciate you stopping by. Adios.